contract, then that contract itself has the ability to set a gas limit. So if, let's say, I send a message to contract A with 30,000 gas, contract A needs to send a message to contract B for some reason. Contract A can specify a budget. It says contract B is only allowed to consume a maximum of 10,000. If contract B consumes less than 10,000, then everything's fine. If contract B consumes 10,000, then contract B gets reverted, but not contract A. Contract A is fine because it's not his fault. But contract B's, but the gas is still fully consumed. So that's the other sort of property. So so every contract has a sort of measure of safety in terms of how much how much gas it can lose if some subcontract that it's calling ends up being in the load. So that's basically how gas economics work. So Ethereum blockchain. So it's a bit more complicated than the Bitcoin blockchain. So Bitcoin blockchain, all you have is a Merkle tree, and that Merkle tree records what all the transactions are, right? And if you want to have any idea what the current state is, you have to theoretically process all the blocks yourself. Ethereum blockchain is a bit different. So we use a data structure that's called a Merkle patrician tree to keep track of the state. So Merkle patrician tree, you can think of it as being kind of like a Merkle tree, but it's more complicated. The idea is that instead of just storing a list of transactions, it actually stores a key value map representing the entire state of the database. So exactly what the current ether, the current code, and the current storage of each individual account in the system. And for the storage of each individual account, that itself is another sort of Merkle patrician tree. So you have kind of two levels. So the point of the other key point is that the Merkle root of the Merkle patrician tree has to be put into the block alongside. When you produce a block, you have to put in the Merkle patrician tree root of the block after you process all the transactions. So, and if you put the wrong root, then even if all the transactions are valid, your block is invalid. Right. So a key point is, so the idea here is basically that the Merkle patrician tree is a structure that allows you to, theoretically, if you are willing to trust some recent set of blocks, and you've seen some blocks and you know that those blocks are valid, then theoretically you could just take the state root and you can actually just download the entire Merkle tree from that state root, just by repeatedly looking up hashes, and you don't need to process the entire blockchain before that. So it makes, it creates it's a sort of potentially a much faster bootstrapping process. That's one reason to do it. So I guess the existing numbers that we have, I actually just got these from Ripple yesterday, that their current databases, or the entire set of data that Ripple has is, I believe, something like somewhere between a few hundred gigabytes and a terabyte, but the size of the current state is less than a gigabyte, because most of the data that it's storing is just history, and if you're just joining the network, you don't even need some auto-processing history. Anything you want to add there?
No, yeah, you don't need any history. You just have to trust that no one modifies the existing ledger without taking into account the entire history.
Yeah. Right. So the other nice thing about a Merkle patrician tree is that it's very fast to update. So theoretically, if you want to remove some node, or if you want to add a node, or if you want to modify some node in the tree, then all you need to do is you need to change that, and you need to just recompute the hashes going just up that particular branch going to the state root. So if you have a patrician tree with maybe 1 billion nodes, then you might only need to make 30 modifications to the tree in order to recompute the Merkle tree root for the new tree after that change. So this is different from Merkle tree, because in a standard Merkle tree, the way Bitcoin works, now you can modify transactions efficiently. So if you just modify a transaction, then if you're modifying it in place, you can sort of propagate the changes up. But if you want to sort of stick a new transaction in the middle, then all of a sudden the entire structure of the tree has to change, and so you have to reorganize everything. Here, each individual modification is very fast. So the other nice thing is that this idea that you have to sort of store the Merkle tree for the state for every block. It might seem horrendously inefficient, because you might think at first glance, well, okay, if the entire state is 500 megabytes, you have a block every 12 seconds, then if that might mean that you're storing 500 megabytes for every 12 seconds, and isn't that going to get very, very big, very, very fast? The answer is no, because once again, the Merkle tree is this nice sort of functional data structure where what you can do is you can say, okay, if I have the Merkle tree in some previous block, then for the next block, in all of the parts of the tree that haven't been modified, I'm going to create some new tree nodes and I'm going to store them. For the parts of the tree that haven't been modified, I'm just going to point right back to the place I'm storing the Merkle tree for the previous block. So at every step, you only need to store the change. You only need to store the changes. You don't really need to store everything. So that's basically a key reason why. I mean, that's the reason why the Ripple database is a terabyte and not a petabyte, I believe. So, and, you know, Ethereum is doing this as well, of course. So it's. And by the way, I do want to thank Ripple for actually coming up with a lot of this. We actually basically. The idea of using a patrician tree in Ethereum actually came from Ripple, so thank you. So, in general, the idea behind Ethereum is that everything is a contract. So, name registry is just a contract that updates an on-blockchain database, and the contract has sort of register operation. So what that means is that if you call the contract with some certain data fields, then you can register a domain and some code executes that corresponds to the database being filled up with the names you're registering. You can create a currency inside of Ethereum, and the way you create a currency is you just take you take the basic definition of what is a state transition for a currency, and you just sort of turn it into Ethereum code. So I'll provide some very quick coding examples after this, just to sort of show the general idea. Decentralized exchange, you could so this is actually interesting because a decentralized exchange, once again, it is just a state transition function. It's something that says you have the ability to place an order, you have the ability to fill an order, and for all of those operations, they can be valid or invalid. And if they're valid, then they do something, they perform some modification to the state that gets stored for later on. Theoretically, you could do more complex financial contracts and a whole bunch of other things. And eventually, the other nice thing is that about this kind of setup is that you can. I'll show this nice diagram that I have in our development tutorial, because it really is nice. So over here, let's say, so here's just sort of complex example that I'm going to use to just describe some of the different ways in which contracts in Ethereum can interact. Now, they theoretically can't do everything. So suppose that there exists a currency, we'll call it Gavcoin, and Gav actually has created a currency called Gavcoin in Ethereum. Is it going to be up for 1.0?
Of course.
Excellent. So, and how do I purchase one Gavcoin?
It's going to have a very interesting currency mechanic, but I'll say no more at this point.
Okay. He's just going to distribute it all to good shareholders. So, based over here, let's say that we have a bet, and let's say that there is Bob, and what Bob wants to do is Bob wants to make a bet against Alice, and he wants to make a bet that the temperature in San Francisco will be greater than 2,000 degrees. The reason is that basically Bob is some crazy robot, and for some reason his code is broken. So let's say Bob is also paranoid, and Bob theoretically wants to use custom cryptography to protect his account. So he wants to use something called a Lamport signature. So over here, instead of Bob talking to a bet directly, what Bob's going to do is Bob is going to send a message to something called a forwarding contract. And a forwarding contract is basically something, it's like something that sends transactions to other contracts on your behalf. And the reason why I want to have a forwarding contract is because the forwarding contract can impose certain restrictions for you. So you can be a bit safer because you don't just need, because the forwarding contract can control sort of, it could try to set limits, it could try to set special conditions. In this case, it actually requires Bob to supply a valid Lamport signature, not just a valid SHA-3 signature. So. Or valid ECDSA signature, so that makes Bob a bit quantum proof. So if Bob sort of sends a message to a forwarding contract, and that message says, hey, please send a message to, and what the message that Bob sends to a forwarding contract basically says, hey, forwarding contract, please send a message to a bet, to this bet contract, saying that I want to initialize this particular bet. The forwarding and by the way, here's some extra piece of authorization data, like a signature. The forwarding contract checks the authorization data. If it's valid, then the forwarding contract immediately sends off the message to the bet saying, hey, I want to create a new bet. So the idea is that the forwarding contract is actually the thing that has relationships with other nodes on the Ethereum network, not Bob. So the point of this is just to show how, theoretically, contracts can have relationships with contracts in exactly the same way external users can. Now Alice is also paranoid, but instead of Alice being paranoid about quantum computers, Alice is paranoid about her private keys getting hacked, and so she's using a multi-sig account. So let's say Alice here has 3 externally owned accounts, so 3 private keys, and she has a forwarding contract. Now over here, what the forwarding contract says is it's only going to forward messages if they receive authorizations from at least two of these three externally owned accounts. So what Alice says is Alice wants to accept the bet from Bob because she knows that the temperature in San Francisco is going to be less than 2,000 degrees. So what she says, she creates a message to the bet saying, "Hi, I want to accept Bob's bet and take the opposite side of it." And so Alice sends a message to the forwarding contract saying, "Hey, forwarding contract, please register that I want to send this particular transaction to this particular address." Then Alice sends a message saying to the forwarding contract from her first account, saying, "Hi, forwarding contract, I want to authorize this particular transaction with this key." Then she does the same from, say, number 2. "I want to authorize this transaction from this key." The forwarding contract keeps track of how many authorizations there are. Now that there's 2 authorizations, it sends off the signature, and the forwarding contract sends off a message to the bet saying, "I want to accept this particular bet." Now later on, some day comes, and it turns out that the temperature in San Francisco is only 14 degrees, a bit less than 2,000. So what the contract does is, so there is a weather data feed. We'll presume there is some kind of entity, let's say the National Weather Network, which is pumping data into this Ethereum contract. It's pumping data of what the weather is in just about every city. So Alice won, and so once again she goes through the same dance, and eventually the forwarding contract sends off a message to the bet saying, "Hey, I think the bet resulted in my favor. Please give me the money." Now the bet, it checks, okay, I wants to check whether the bet resolved in my favor or not. So it wants to know what the temperature is in San Francisco. Hey, weather feed contract, please tell me what the temperature in San Francisco is. The weather feed contract replies, 14. The bet says, okay, 14 is less than 2,000, looks like Alice wins. Now of course, Alice and Bob, they're not actually making the bet in Ether, they're making the bet in Gavcoin. So the bet says, so instead of just sending Ether to the forwarding contract, what the bet is going to do is it's going to make a transaction or a message to the Gavcoin contract, and it's going to say, hey, Gavcoin contract, please register myself, or please transfer some 100 Gavcoin from myself to Alice. Now the myself is of course the actual bet. So the bet contract itself actually has an account with the Gavcoin contract, once again, and it transfers its Gavcoin over to Alice's forwarding contract. So, look, this is basically about as complex as we're probably going to get in the first year. Point is to just sort of show how you could have all these different things that contracts can do. They're sort of like modular units, programming units, and theoretically you could code all these up individually. We can all interact.
Just
Yes.
a quick question about the weather feed. How does that play into the smart contract? So is it able to go outside its system?
No. So in this case, it's just some trusted weather feed. So the National Weather Network has a contract which says only if a transaction is coming from a private key, which is known to be connected with the National Weather Network, then I am going to update whatever data feed the transaction wants me to update to whatever value. So if it's not, then it's not. So this is just a simple centralized approach. The other approach you could take is you could have multiple data feeds. You could use this crazy thing called shelling coin, which you're probably not nearly going to get into. That's basically the idea. So, in general, this is sort of this is the path that the execution might take. Bob sends a message to the forwarding contract. So the other point is that these messages, they actually have return values, right? So when you call a contract, or when you send a message to a contract, that's actually kind of equivalent to calling a function, right? So when you send a message to a contract, the contract does a computation, it can actually return a value. So over here we have Bob's calls the forwarding contract. The forwarding contract then asks these other contracts and says, hey, is the signature valid? The signature verifier replies yes. Then Bob sends off a message to the forwarding contract. So in this case, we're going to assume that Bob won this particular bet. Then the bet sends a message asking the weather feed. The weather feed returns a value. Then the bet sends off a message to Gavcoin. The Gavcoin might return success or something, but in this case it doesn't really matter. So sometimes you don't really need the return values. And in this case, the bet might return success or failure. You could have whatever conventions you want. And the forwarding contract, it doesn't really need to return much of anything. So so the computation, so on a sort of more low level, the way the state machine in Ethereum works is there's a sort of stack-based bytecode code language. It's kind of similar to Bitcoin script, it's kind of similar to Forth, it's kind of similar to traditional assembly language, it's this weird hybrid of a bunch of things. So a program in Ethereum, it's a sequence of opcodes, so it looks kind of like this. Push 1, 0, call data load, S load, not, push 1, 9, stop, push 1, 32, call data load, push 1, 0, call data load, S store. So, anyone want to guess what this particular contract is supposed to do? It's a name registry. So, let me go through this carefully. So let's say that, so the way that this works is that anyone can send a message to this contract which containing 64 bytes of data. So we assume that the first 32 bytes of data represent a key, and the second 32 bytes of data represent the value you want to register. So the key could be, some value, some kind of mydomain.eth, and the value could be some IP address. So in the transaction data, the first 32 bytes are the key, the second 32 bytes are the value. So what do we do? First off, if we look, so in general, the state, the thing that the Ethereum virtual machine keeps track of is it keeps track of this number called a program counter, which basically just says where in the code do we look for the next instruction. It has a stack, so a stack is just a stack of values. Then there's something called memory, which is kind of like temporary scratch space, and there's storage, which is permanent storage. So in this case, the first instruction that we had in our little script is push 1. So push 1, and it pushes a 1 byte value. So in this case we're doing a push 1 of 0. So that basically just pushes 0 onto the stack. So we have 0 on the stack. The next instruction that we have is call data load. So what does this do? Basically, what call data load does is it takes the top number from the stack and it returns the value in the transaction data at that particular index. So it returns the 32 bytes at that index from. So over here we're going to assume that that we have 64 bytes of data, where the first 32 bytes of data encode the number 54, and the next 32 bytes encode the number 20, 20, 20, 20, 20. So the first 32 bytes here, so it returns 32 bytes starting from 0, so it returns the value 54. So now we have 54 on the stack. Now the next opcode we have is sload. So sload, what it's doing is it's going to pop a value from the stack, and it's guess which key it's going to pop from the stack, or well, it's going to pop the top value from the stack, and it'll push the value in contract storage at that index. So the stage where we're at in the code right now is, the way name registries work is they go into the database and they check, well, the first thing you check is the value at this particular key taken already. So in this case, the key we're trying to register is 54. The value we're trying to register is 20, 20, 20, 20. So basically, up to here, all we did is we just loaded the number 54 onto the stack. Now we're going to actually grab the value from the stack at index 54. Guess what? It's 0. It looks like nothing's been registered yet. And now what we do is we say now. The thing we're actually going to do is we're going to say not. So the point of not is, the point of the not opcode is that it converts 0 to 1 and it converts everything that's not 0 to 0. So basically the thing is that in a registry contract, what we want to know is whether or not whether a key has not been registered, right? So over here, we've discovered from our little sload opcode that the value in the storage at key 54 is 0. 0 means it's not registered. So if we apply not opcode, the answer to whether it has not been registered is yes. So over here we have 1. Now we just have push 1, we push 9 onto the stack. Now we have an instruction called jump I. So jump I is basically kind of like a conditional jump. It says if the value that's sort of that's 2 values deep into the stack is not 0, then we jump in the code to the index that's the top value in the stack. So if the second value is not 0, then we jump to 9. If this value is 0, then we do nothing. So anyone want to guess what the point of the jump, why we need to have this sort of conditional jump in the code? basically, what is the name registry contract doing? So like, what is the sort of fundamental logic that it's implementing?
If the name hasn't been registered, save it.
Right, if the name hasn't been registered, save it. So if the name has been registered, then what do we want to do?
Returns an error.
But we want to, well, basically over here we're just jumping to the part in the code after everything else. So, yeah, one option is to just return an error. Actually, no, right, actually no. So the thing here that we're doing is we're checking if it's unregistered. So because it's unregistered, we're going to jump to 9. So if we go back to the code over here, so we see push 1, 0, so we see push 1, 0, call data load, SLO not push 1, 9, jump by stop. So if, let's say, so over here we have 54, over here we loaded the storage at 54, and over here we determined that the storage at 54 is not empty. So if it's not empty, then what we're going to do is we're going to jump to index 9, which is over here. If it is empty, then the jump would not have jumped anywhere, and we will just walk right into the stop opcode. And so that's basically.
So if you reject a request to register a name because it already exists,
Yep.
does the person end up paying anything? Because is there a transaction record?
Yeah, the transaction still goes into the blockchain. The transaction is technically still valid, and so we still end up paying. Yeah, so if it's invalid, then you just whack your way into a stop, and that's it. Now, over here, now let's suppose that everything in our execution, everything's fine. We managed to jump over to index 9, and so we're over here. Now, what are we going to do? So the jump I got rid of the 1 and the 9 from the stack. So it starts off by pushing 32, and we do call data load. So why do we want to push 32 and then do a call data load? So what does call data load do again?
Looks to see where that number's pointing and loads the data from.
Right. It looks to see what the value is in the message data at that particular index. So over here it looks, so we have 32 bytes for the key and we have 32 bytes for the value. So here we have the 32 bytes for the value that start from index 32. So over here we have the value 2020, we load that. So this is the value we actually want to set at that index, right? So now what we're going to do is we're going to push 0, and the reason why I want to push 0 is because we want to load the message data at index 0. So the message data at index 0 is supposed to be what again? The key, exactly. The message data at index 0 is the key, the message data at index 32 is the value. So here we have the key, here we have the value, and we just use an opcode called store, which stores the value in storage at the index, which is the key. And we're done, mission accomplished. So this is basically as low level as you could get. In reality, of course, we actually have much more intuitive languages for programming this sort of thing. So the code that the code that compiles to this would actually be, hold on, it might actually be a bit lower here. Okay, GUR doesn't mention it here, but anyway. You don't want to know how do we turn on a text box in here?
What do you want?
Some kind of text box, just to write code quickly.
I can give you Emacs or text.
Text edit is fine.
Just yes, there you go. Okay.
Hold on, file new.
Yeah, maybe you can close that one there.
Sure. So in our we have a couple of languages. So Gav is going to be showing off Solidity. So